Okay, Brooke, here you go. This is just, hopefully this will help clear some stuff up about the summation notation. Say hello to Santiago and Muhammad if they're in your class as well. So this is the typical definition of an integral. And so the integral from a to b of some function f of x defined in terms of x is equal to the infinite sum from 1 to n, where n's headed to infinity, of f of x sub I delta x. So let me just pick this apart just as a reminder of what all this is. This part of the integral is a Riemann sum, okay? And so we can do an infinite sum where n's headed to infinity, but in a minute we're going to look at the example that Professor Flores gave you, where they just say they want 6 subintervals. Delta x is the width of the subinterval, and so it's defined to be delta x, the width of each rectangle, is defined to be b minus a divided by n, where n is the number of subintervals. So a to b is how far apart you're taking the interval. Let's see. N is the number of subintervals, and f of x sub I is the height of each rectangle. So the star means that it is can be from anywhere in the subinterval, but lots of times we'll take it from the right endpoint. In our class, we took it from the right endpoint. Sometimes we took it from the left endpoint, and sometimes they'll take it from the midpoint. And so later in the PowerPoint that you received, they talk about the midpoint rule. So in general, this is the definition of delta x. N is the number of subintervals. So if we're doing this, so this means we're going from a to b. The sum of these, this x sub I, x sub 0 is where a is, and b is what x sub n is. All right. And so if you take endpoints from the right, let's take note of this. If you decide to take your endpoints from the right, then f of x sub I turns into, instead of the star, if we're taking it from the right, then this turns into f of a plus I times delta x. This becomes important when we hit that example where we use the summations. Okay, so that's just a little bit of a reminder of what all these little parts mean. And this is the f of x sub I that you use if we are using the right endpoint to determine height, to determine the height of the rectangle. In a minute we will do a Riemann sum with 6. Okay, now separately, this is something that we could have learned in pre-calculus, but in my class I didn't go into all this detail. I really didn't realize you would be needing it. So let's go through it now. Here are some summations. Let me make sure you can see this. Yeah. So these are just some formulas of summation. So if you are let me show you how this works. If you're taking a sum from I is 1 to n of just I, this is a nice little formula you can use instead of doing this addition. If you're taking the sum from I is 1 to some number n of I squared, instead of adding up all these numbers that are being squared, you can use this formula, and the same for this. These are just some nice formulas we can use. So for example, if we let n equal to 5 in this top one, let's just see what happens. Okay, so if we let n equal to 5, if we were just doing the regular sum, this would be the sum from I is 1 to 5 of I. What that would be is let I be 1, then let I be 2, then let I be 3, 4, all the way up to 5, and we would add up these numbers. And if we add up these numbers, we'll get 5 plus 4 plus 3 plus 2 plus 1, and if you add those up, you see that you get 15. Okay, now what if we said let's just use this formula? Okay, let's do that. So if we have to add from I is 1 to 5 of I, use the formula. Keeping in mind that n is 5. That is 5 times 5 plus 1 is 6 divided by 2. 2 goes into 6 3 times. 5 times 3 is 15. It is simply an alternate way to get this sum if you want to use that formula. So the same thing applies for I squared. For instance, let's let, just to see how this works, let n equal to 4. All right, if we let n equal to 4, then if we're going to sum from I is 1 to 4 of I squared, this would literally be, let I be 1, okay, 1 squared. I is 2 plus 2 squared. I is 3, 3 squared. I is 4, 4 squared. So that would be 16 plus 9 plus 4 plus 1. 1 squared is 1, 2 squared, 3 squared. So that's going to be 20, 30. This is going to be 30. Okay, by formula, we could do that. The sum from I is 1 to 4 of I squared would be 4, because that's what n is. 4 plus 1. 2 times 4 is 8, plus 1 is 9, divided by the number 6. So I'm going to simplify this fraction. Let's see. 2 goes into 4 2 times, 2 goes into 6 3 times, 3 goes into 3 once, 3 goes into 9 3. So we end up with 2 times 5, which is 10 times 3, we get 30. Okay, we can do the same thing here real quick. Let's let n be 3 for this last one. And this is simply a formula. If we did the straight sum, the sum from I is 1 to 3 of I cubed, we say, okay, I is 1, 1 cubed. I is 2, 2 cubed. I is 3, 3 cubed. So this tells us how far we add, right? 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So if I add up this, I'm going to get, what am I going to get? 27, 28, 29, 30, 1, 2, 3, 4, 5, 36 is what I'm going to get. Okay. By formula, we could say, okay, the sum from I is 1 to 3 of I cubed is the same thing as this formula. If n is 3, we'll say 3 times 3 plus 1, 4 over 2, the whole thing squared. All right, 3 times 4 is 12, divided by 2 is 6. This is 6 squared. This is 36. So that's what these formulas are. They're just a nice formula that you can use instead of having to add up a bunch of numbers. Now, also, I think that you guys learned about, in the PowerPoint, I saw this, and so this is just more summation laws. Why Professor Flores is talking about summation laws, or why any professor would, is because integrals are summations. And so the laws that apply to these sums also apply to integrals. So that's why he's going through this. So this basically says if you're taking the sum of just a constant, that's equal to the constant times the number of times you're summing it. And you can try that out. You could, just like I just did, you could pick a number for C and pick a number for N and try that out. This says if you are taking the sum of some expression with I and it's being multiplied by a constant, you can just move the constant in front and then take the summation of that expression. If you are taking the summation of two different expressions, you are allowed to split those up and sum it one here and one there. So this is the same as the integral rule. If you've got an integral of a plus b, two expressions in x, dx, right, we'll say this is in x. This is the same thing as the integral of this plus the integral of this. You have seen these laws also with limit laws. The sum of limits is the limit of sums. Same thing here. If you're taking the difference, you can split that up. That's all that's saying. Okay, now I'm going to stop this video and we're going to start looking at example 2. Oh, here, let me go through example 1 real quick. Example 1 has to do with kind of with what he had talked about. This is example 1 in the PowerPoint. Okay, so it said express the limit as n goes to infinity of the summation from 1 to n of this expression, x cubed, x sub I cubed plus x sub I times sine of x sub I times delta x. Okay, delta x, I see you can't even see what I'm talking about. Let me move this guy down. Okay, delta x, sorry, example 1 from your PowerPoint says this. There was, I think, a little typo on the PowerPoint, so I think there was just like a number 1 instead of a plus right there. And so if you had a question about that, that's just a little typo that happened. Since they wanted the integral to go from, the sum to go from 0 to pi, that's your limits, your lower and upper limit, a and b. Instead of writing x sub I, you just write it in terms of x, and the delta x becomes the dx. So that's example 1. I'm going to split up this video, and then we'll take some time to look at example 2.